Hello students, welcome back. We completed these two, this one and that one, and then one more to go. Third one here is just a trivial application of the second. Just take the square root, then you're gonna get this, so no big deal there. So let's work out the fourth expression here. Okay, let's prove that. So what's the definition of the variance? It's here, isn't it? Deviation x minus mu square times the probability and then add them all up. Yeah, that's the variance. Okay, alright. And then let's do some algebraic manipulation. This is just complete square. So this thing squared minus 2 mu xi plus mu squared. Let's align. Okay, is everybody happy? Just complete square, nothing more. Just FOIL out. This is what you're going to get. And then let's distribute pi's in there. So this one times pi, that times pi, and that times pi, and I don't need this one anymore. And let's align. Okay, let's separate the summation again, because add this bunch and then the next bunch and then the next bunch and then adding all those later versus adding all these and then adding all these and then adding all these. That's the same because addition is commutative and associative. So we can do this. Okay, all done. Edit this part, edit this part, edit those parts, all separately, and I'm adding all those. Okay, nearly done. Now the first expression here, what is this? This is nothing more than expected value of xi squared. You see, it's nothing more than this times pi, and here, it's just x squared. So this whole thing here is expected value. Let's keep it at that. Let's keep it at that. And now let's work this one out. 2 mu, these are constants, so let's take those out. Alright, 2 mu times xi times pi, what is this? Payoff times probability and then adding them all up. Oh, this is the expected value. Alright, next. Mu squared is constant, so let's take it out. It's distributive law. And then times pi. And what is this? Sum of all probabilities for all is going to be 1. Let me write one more line. So this whole thing is expected value of x squared. And okay, looks like I'm in the right track. Now this is expected value, isn't it? X times pi, all those, and then add them all up. So that's times mu. And now sum of all those times 1. So what do you have? This is all set. and 2 mu squared plus mu squared. I don't have to use write times 1, do I? Never mind. Oh yeah, I don't have to write times 1. And this is mu times mu, so, oops, squared, yeah, let's write like this. So this whole thing now becomes minus mu squared. 2 mu squared plus mu squared, so just minus mu squared. And then what is mu, by the way? That's the expected value. So this is actually expected value. And that's precisely what we wanted from the very beginning. Let's align a little bit. Okay. Expected value of square minus square of the expected value right here. So that's a property of variance. Variance is expected value of square minus square of the expected value. And that completes the proof. Okay, all right. Now, another one here. Now, if I define a random variable, a composite random variable like this, then it turns out the expected value of this new random variable is 0, and then the standard deviation is 1. Actually, variance is 1, so square root of variance is square root of 1, so standard deviation is 1. So we're going to prove that expected value is 0, and the variance is 1 for this. And then, of course, we can use the properties of expected values and variances. And then that's nothing more than, let's see. Let's see, did I manipulate correctly? All right. And then I can apply this one, right? So this is 1 over sigma times expected value of x minus this one, just that. And what is this? Expected value. That's mu. So this is mu over sigma minus another mu minus sigma, and that's 0. So we can just use this, and remember expected value is mu, and then you got it. So whatever random variable x is, if you calculate x minus mu over sigma, where mu is the expected value of x and sigma is the standard deviation of x, then this new random variable z obtained by this composite expression has expected value 0. So this is kind of like adjusting the 0 point. And one of my favorite analogy here is temperature conversion. You see, if x is Fahrenheit temperature, then how do you convert it into Celsius? X minus 32 degrees over 1.8 is the Celsius degree. And then Celsius is, of course, the one we use in all kind of scientific computation, because the 0 point is precisely at the point that a clean water freezes, or vice versa. Okay, alright, so much for expected value. How about the variance? Can we apply the same idea here? Yeah, I guess so. You can rewrite it like this. And then for variance, this plus b part drops out. That one just drops out. And then we're going to get square, right? 1 over sigma squared. And then variance of x. But then again, what is variance? What is standard deviation? Standard deviation is sigma, so variance is sigma squared. So we get sigma squared over sigma squared. And that's what, oops. And that's 1. So we have the proof for this one as well. So, what's the moral of the story? For any random variable x, if you do a bit of a manipulation using its expected value and standard deviation like this, x minus mu over sigma, you're going to get a new random variable z that came from x, so it shares most of those properties of x, but with these nice properties. Expected value is 0, and the standard deviation is 1. Variance is 1, so standard deviation is square root of 1, so it's going to be 1. And this expression will turn out to be very, very important in the next module, and as a matter of fact, until all the way toward the end of the semester. And therefore, I sometimes write this problem in the exam, but not for a discrete random variable version. And I usually write it for a continuous random variable version, where you have to use some integral computation, because that's more important in general. And yes, that's more important and that's more general. So this version is, yeah, it works, but for special case, discrete case, a little bit less important case, but still, good thing to remember. By the way, there's some relationship between the population mean versus expected value when we have the property, when you have the probability as a relative frequency, and here is the full proof actually. This f1 is the frequency, the number of repetition of x. And then population standard deviation and probability standard deviation is the same as well. You see, we have all those deviations squared, but then again, many are repeating. Those are frequencies, f1 through fn, but f over n, that's a probability. In that case, what do we have? Same as the probability variance. So probability variance and then population variance are the same. So upon taking the square root, population standard deviation and probability standard deviation are the same. Sample standard deviation is different story. I have n-1 down here, not just n, so that makes the big difference. And that's where I'm going to stop here. I don't know whether I'm going to use a lot more of this expected value expression for composite random variable any more than this, so I'll stop there. Thank you.